Hi, I'm Xin. I'm presenting our work, Learning Fine-Grained Visual Understanding for Video Question Answering via decoupling spatial temporal modeling. Video question answering is a task that machines have to answer questions about videos. It involves diverse information, including objects in scenes, human dialogues, temporal relations between events, or even high-level cognition. State-of-the-art approaches often adopt the framework of pre-training and fine-tuning. A model first learns the interaction between video and language with the objective like matching, contrastive learning, or feature regression. Then it is fine-tuned for different video language tasks, like retrieval and video question answering. However, although this framework has made a great progress, these approaches are not fine-grained enough for understanding scenes and temporal relations in terms of spatial and temporal modeling. For spatial modeling, most video language models are not fine-grained as image language models. Image language models encode grids and regions with attentions, but video language models often use static frame features or pre-extracted action features from multiple frames. In fact, we don't need video language models to answer questions about scenes, because if a question is only about spatial information and has nothing to do with time, the answer is usually consistent across all related frames, like the example here of a man playing a guitar. These kind of questions can be seen as image QA. An analysis shows that if we average the frame-by-frame prediction of an image language model, like LBAF, it performs really well on some categories about spatial information. It shows the potential of using image language models for spatial modeling. Besides, existing temporal modeling is also not fine-grained enough. From these example questions here, we can see that a model has to recognize events in videos and build the temporal relations between these events. For example, an event happens before or after another one. But some pre-training approaches are like a video with a sentence description. We may lose details if they are not mentioned in this single sentence. For example, from this caption here, we cannot know what happens after the woman hit the ball. Some work are like short clips to dialogues, but because people can talk about anything not related to the scene, the alignment is noisy. For example, in a video about a woman teaching yoga in the park, when she talked about the concert held in the park, or when she explained the yoga pose, the transcript and video content are not aligned. Some other work generates pre-training data from video captioning datasets, but this approach is also limited to scene and spatial understanding. We did another analysis by picking one approach from each kind of pre-training strategy and test their performance of temporal modeling. We train a model with normal input and test it with shuffled frames. The performances are similar. This tells us the recent design of temporal modeling can be improved. Next, we are going to present a new pipeline and pre-training strategy for fine-grained spatial and temporal modeling. We have discussed before that image language models can encode more fine-grained spatial information, so we propose a decoupling strategy. We encode spatial information with image language models and encode temporal dynamics with video language models. We can bridge image QA and those video QA with scene understanding by even pre-training the image language model further with image QA. Here is the overall pipeline. We call it decoupling spatial temporal encoders. The left stream with the image language encoder encodes the spatial information. It processes frames at high spatial resolution independently of time and averages the prediction results of each frame. The right stream with the video language encoder encodes temporal information at high temporal resolution. To train a video language encoder for effective temporal modeling, we propose a novel pre-training objective. To encode temporal relations, a model has to understand video as event sequences, associate the temporal relations of events with time conjunctions, like before or after, and transfer well to video QA. So, we generate many questions asking temporal positions of events in videos. For example, in a video with two events, A and B, we ask the model what happens after event A. The model should give the answer event B. The data for this pre-training strategy should provide descriptions of video segments. Ideally, the text of dense video captioning fits our need well, but many segments in this dataset overlap, and temporal relations are ambiguous, so we synthesize the pre-training data. We name this objective temporal referring modeling. We first sample videos from video captioning dataset and concatenate these videos, so we can have description perfectly align with all video segments. We then fill up the question templates asking what happens at the beginning, at the end, before, or after an event. These designs bring us two benefits. We can fully control the temporal relations and have aligned descriptions. We leave generating video with smooth transition and support of high-level cognition for future work. We estimate our modeling design and pre-training objective on two datasets. The first one is a widely used benchmark, ActivityNet QA. It contains diverse question types including both spatial and temporal understanding. We surpass previous work with much less pre-training data. The second benchmark is AGQA. Its questions are mostly about temporal relations and have extensive annotation. We surpass previous work with and without pre-training data. We also do the evaluation study. Adding frame and video inputs are indeed helpful. Pre-training with image QA on our temporal referring modeling can improve the model capacity further. Another evaluation study tests the individual capability of our two streams. It shows that our model is not a trivial ensemble. In summary, existing video language encoding is not fine-grained enough. We propose a hybrid pipeline, decoupling spatial temporal encoders. It composed of image and video language models. To learn temporal relations, we propose a pre-training objective temporal referring modeling. The model has to identify events with their temporal positions. With these two designs, we outperform state-of-the-art approaches on two benchmarks with much less data. Thanks for watching.